Okay, all right. So let's continue now with local search. Well, let me just share the. All right. So in this fifth lecture, I want to talk about local search, and if we have time, I want to go into GRASP, which is Greedy Randomized Adaptive Search procedure. If we don't have time, then I'll go through that. So the idea is to look at some basic local search elements in terms of defining a neighborhood, what we mean by neighborhood, how we perform neighborhood selection, go through an example of a classical local search, and then also mention some potential for local search improvements before we go on to GRASP. Again, looking at our illustration of various categories of different optimization methods, local search fits into the category of improvement metaheuristics. So we have some kind of a solution which we're now iteratively trying to improve by applying some kind of local transformations to it. So once we obtain a local optimal solution, we are done. So local search in its simplest form gives us a locally optimal solution. This is a generic approach, and as I said, there are many variations, and often they're used in combination with or variations are in terms of more complex single solution based heuristics such as taboo search, GRASP simulated annealing, which we'll get to later on. But what I want to go through here now is just the simple, let's say, ideas behind a local search algorithm. So we need to define what we mean by the term neighborhood. We've now used this term many times. How we can obtain an initial solution. So when we talked about greedy algorithms, we start with nothing and we construct an initial solution, for example. Here, when we talk about local search, we assume we have some kind of an initial solution, or we obtain an initial solution, for example, either randomly or using some kind of a greedy heuristic, and then iteratively try to improve that solution. What we need to define is how are we going to improve the solution? So what are these local transformations that we're referring to here? Over here, how many of these potential solutions are and how we're going to select now, let's say, potentially a new solution and advance the search. So in a very at a very high level, what the pseudocode would look like is we generate an initial solution. That's our current solution. From this current solution, we generate a set of candidate neighboring solutions, and we'll specify what we mean by neighboring solutions. We choose a better neighbor or the best neighbor, and there are different also strategies for this, that will become the new current solution if it exists. If there is, out of all of the neighboring solutions that we're searching for, if no better solution exists than the one we currently have, we're done. So and we keep doing this while we continue to find a better solution. What we mean by done is that means that we've checked all of our neighboring solutions. There is no better solution, which means we are currently in a optimum or local optimal solution. It doesn't necessarily have to be the globally optimal solution, but a locally optimal solution. When we're looking at this neighborhood, so we say we have, let's say S is our current solution. Let's say this is some kind of a binary vector. We generate some kind of a subset out of all of our potential solutions. We generate a set of candidate solutions, which we define as being the neighborhood. Let's say we specify our neighborhood, if we have a binary vector, as being all solutions which are 1 bit difference from the solution we have. So if we have a solution, let's say 1, 1, 1, 1, neighboring solutions would be a 1-bit flip, for example, 0, 1, 1, 1, or 1, 0, 1, 1. So anything that is one bit flip away would be contained in this neighborhood. So this is actually a subset of our complete search space. So we'll check this neighborhood solution. We'll evaluate each of these neighboring solutions in terms of their fitness or this evaluation function, and see, is there a solution here that is better than the one we currently have? If yes, we select that solution. That becomes the new solution. And again, we generate the neighborhood of that new solution, check, is there a better solution than the one we currently have, and we keep going while there's still a better solution than our current solution. So the idea is that, as I said, we advance the search until we reach some kind of a locally optimal solution. When we say neighborhood, again, this neighborhood, and usually it's denoted as N of S, of a solution S. So I have a certain solution which is a part of my overall search space, S. The neighborhood contains all solutions that can be obtained from my original solution by applying some kind of an elementary, we refer to this as a transformation or perturbation called a move. As I said, an example for a binary vector would be a 1-bit flip. If I have a permutation, let's say a traveling salesman problem, and my solution is representation includes a permutation of n cities, I can say that a neighboring solution would be any solution that involves simply swapping 2 cities. So let's say swap the 1st and the 10th city. Simply swap them in terms of this permutation vector. That's one neighboring solution. Any such swap, but only one swap, contains then all of my neighboring solutions. So what I'm doing actually is this function n is mapping from this search space. I'm actually deciding y2 to this. For each solution in the search space, I'm deciding whether it is a neighbor or it isn't a neighbor. That's the size then. So S is this neighboring solution it's part of the neighboring solution if, again, it can be obtained by applying this kind of elementary move or transformation that we define. If we're looking at a continuous neighborhood, and this is just a simple illustration of in 2 dimensions, then the neighborhood will be some kind of a continuous ball with a center. This is my current solution, and I can say that with respect to, let's say, these 2 dimensions, anything that is within this radius of epsilon far away from this solution is going to be within the neighborhood. So that's intuitive. Of course, if it's a multidimensional solution space, then we can define some kind of a distance in terms of this n-dimensional space. And I'm trying to find, so I'm searching this, I search my neighborhood, I find whether there is a better solution within the neighborhood. If there is, then let's say it's over here, I go here. Then again, I find a new neighborhood, and I go to the best solution. If it's better than if there's a better solution than the one I already have, I move to that solution, and so on. So let's say a classical hill climbing type algorithm would mean that we're continuously moving towards some kind of an increasing value, and we terminate when we reach a certain peak. So we don't look ahead of immediate neighbors. We just look at our current neighbors, and we move to that point. If we're looking at a discrete neighborhood, so we have some kind of a discrete optimization problem, such as this is an example of a binary representation, we can say that this neighborhood is represented by all solutions whose distance with respect to our current solution is less than a certain amount. Now, the question is what we mean here by distance. And in this case, let's say we have our current solution to be this green one, 0, 1, 0. We can say that distance would be, let's say, one bit flip away. So these would be these potential pink solutions are neighbors to this solution because they are one bit flip away from this solution. So in this case, in that essence, neighbors are actually these adjacent nodes in the hypercube, which represent all of these different solutions. If we were to generalize this a bit and say that instead of just binary values, each of these variables can take on a value from a certain fixed sized alphabet, let's say, whose cardinality is k. So we have each of these values can take on a value, one of k values. Okay. And let's say we have an n-sized fixed vector of n variables. Each variable can take on one of k values. What would be the size of the neighborhood? What do you guys think? For a vector that is size n, so I have n variables, each variable can take on one of k, so values. What would be the size of the neighborhood of a given solution? Someone unmuted? We can't hear you, sorry. Is it just me or can anyone hear? Okay, I can't hear anything, sorry. Maybe some microphone problems. Okay. Okay. Oh, sorry, I can't hear. But anyway, so the size of the neighborhood would be k minus 1 times n, right? So if, as I said, this alphabet is of size k, then each value, so for each of these n variables, it can take on, it already has a certain value. It can take on k minus 1 other values. So let's say each variable can be numbers 1 to 10. It can take on 9 different values that are different than the one it currently has. And we do this n times because we have n variables. So k minus 1 times n would be the size of such a neighborhood. Okay, everyone following me? Okay, again, stop me if there are questions, since I don't see or hear you guys, so I have trouble knowing whether if you're following me. Okay, let's look at the satisfiability problem. Again, let's say we have a representation which is a vector of n bits, n is these n are the variables that we're trying to decide on whether they are true or false. And let's say we define our neighborhood as a one flip away. We can change the value. So if we have a solution such as this one here, A, B, C, D, E, so 1, 0, 1, 1, 0, then we have 5 different neighbors or n different neighbors. The size of the neighborhood in that case will be n if we define it as being one flip. Okay. Let's look at the traveling salesman problem. So we have a permutation of cities. Let's say our current solution is A, B, C, D. In the end, we always return back to the initial city. This is an example. The fitness for this value, so if we evaluate this solution, A, B, C, D, and then going back to A, is going to be 9. If we define a neighborhood as being a pairwise exchange, so this is our current solution is A, B, C, D, and we say that we can take any 2 pairs so we pick, let's say, in this case, A and B, and we switch them. So then we pick C and A, we switch them, and so on. We get n times n minus 1 divided by 2 neighbors. Why this number? Well, first we pick, so we have n ways to pick one city and minus 1 ways to pick the next city that we're going to switch it with. And we divide that by 2 because deciding on switching A and B is the same as deciding to switch B and A, right? So that's why we're dividing by 2. Let's look at the evaluation of this neighborhood. So if we have our first solution, we evaluate it, its fitness is 9. We define our neighborhood as being this one switch. So we switch any 2 cities. We have n times n minus 1 divided by 2 neighbors. We check all of the neighbors. We check their fitnesses, and now we can decide on how to proceed. So we can choose, we have, again, 2 solutions which are equivalent to the one we currently have. We can decide to choose one of these. We can also decide to terminate. Depends on now the design of your local search algorithm. Let me go over here for a second. So another common neighborhood or move operator for traveling salesman problem is the 2-opt swap, or it can also be more generalized to the k-opt swap. But what is the 2-opt swap means that we take any 2 edges which are not adjacent to each other, and we cross them like we show here in this example. So we took edges A and E and C and D, and we simply cross them in this manner here. So one solution is this solution over here is A, B, C, D, E going back to A, and over here the solution is A, B, C, E, D, A. So the 2-opt swap is a common move operator used for problems that can be formulated in terms of traveling salesmen. What is the size of this neighborhood? So question. So we take any 2 branches or any 2 edges which are not adjacent, and we cross them. Any ideas? What would be the size of this neighborhood? No? Okay. Go ahead. Okay, I can't hear again. I hear there's some noise.
n-1 times n-2.
Okay, can you explain?
Because we have 5 edges in this situation, but we can't have neighboring ones that are touching. So n-1 would be choosing. Wait, no. No, we can choose. We can n times n-1 because we can choose any edge in the beginning. No, n-2 because we can choose any edge in the beginning, and then we can't choose the edges that are next to it. So it's going to be n times n-2.
Okay, but let's say I take now edge, this one, AB. What are my, I can, so I can choose any, n, I have n edges, so n is the number.
n-3.
Yes. Okay. So I chose AB. Now I cannot choose AB again. I can't choose AE because that's adjacent, and I can't choose BC either. So n times n-3. What else? I'm still missing something. So I chose here, for example, divided by 2. Yes. So the size of the neighborhood in this case would be n times n-3 divided by 2. Okay. Why? Because again, if I chose, in this case, I chose AE and CD, it's the same as choosing CD and AE. Okay, so that's why I'm dividing by 2. Is everyone with me on this? So when you're given, when you think of a neighborhood, or you're trying to come up with a neighborhood to use, it's always good to think of the size of that neighborhood. That's also going to impact the complexity of the search. That's one thing. Another reason why, for example, this operator is efficient in terms of routing problems such as traveling salesman is because it has something called high locality. Which means that 2 solutions, in this case, let's say that we have these 2 solutions that we have shown here, are likely going to be have small variations in terms of the actual solution fitness. Whereas, for example, switching 2 cities will give me a larger, actually, variation. So, for example, for scheduling problems, something like 2-opt swap, actually, where it's very important the actual order in which we're conducting certain things, will probably give larger changes to the actual solution space and be less efficient than, for example, for traveling salesman problem. So this, I mean, the takeaway message that I wanted to say here is that the efficiency of a neighborhood is related not only to the representation, which is in this case some kind of a permutation, but also to the type of problem. So when we talk about scheduling problems, permutations represent some kind of a priority queue. So here, that in that case, the relative order is important. Whereas in traveling salesman problem, it's not the relative order, but the adjacency between 2 cities. So, for example, while the 2-opt swap can give us a large variation for scheduling, it can give a smaller variation in terms of routing problems. So that it's always good when you have a certain problem when you're defining a certain move operator or transformation or neighborhood. Check in literature also what are some examples of move operators that have been used for efficiently for such types of problems. Some other examples just to show you what other examples of neighborhoods. Insertion operator could be, let's say, if I have a solution and I simply take any of these n elements and I insert it into another place in the permutation. So these are examples of operators which are more used in scheduling problems. Exchange operator, I take any two cities or nodes and I simply switch them. So this is different than the two-opt swap where we were talking about edges and crossing the edges. Here we're just taking the two, let's say, cities like we had just in the previous slide with traveling salesman problem, and we switch them. That's the exchange operator. So the important thing is just, as I said, to keep in mind that how that impacts the search space for a given type of problem. Again, when small changes are made in the representation, the idea is for the solution to have small changes. I'll talk a little bit later on about this idea of this fitness landscape and so on. What we want to get is try to get a smooth landscape where individuals or solutions, representations that are similar to each other, tend to behave similarly, so they have similar solutions in terms of solution quality, and that's something that's important. And as I said, I'll get to that a little bit later on. Okay, when we look at when we look at these neighborhoods, an important design issue is the size of the neighborhood, and oftentimes there is this trade-off. So if we have a large neighborhood, then yes, we can check a large area. Perhaps not get stuck in a certain local optimum because we'll check a larger area, find probably better solutions, consider more neighbors in each iteration, and more likely escape certain local optimi. However, if we design a large neighborhood, then computationally it's more complex, of course, to explore it. What's important, and again, I'll repeat this later on, but if we have a certain neighborhood defined, let's say I have my neighborhood, I defined a neighborhood as this 1-bit flip. Or actually, no, wait, let me go back to this traveling salesman problem. I defined it as this, I have an insertion operator. That's one neighborhood. Another neighborhood is this two-opt swap. Different neighborhoods will give me potentially different local optimi that I will get stuck in. So even if I start with the same solution, I apply this neighborhood, I go through this local search algorithm, it ends once I reach a local optimum. The important takeaway message is that that local optimum can be different if I define different neighborhoods. Obviously, because I'm searching the search space using a different, let's say, trajectory. I'm going from one solution to another different ways, right? That's why the local optimum does not necessarily have to be the same depending on, it will depend on the neighborhood that is defined. Okay, so we said the neighborhood size is important. The first step is to try to find an initial solution. And we said before we start with our local search algorithm, we have to start with some kind of an initial solution. Let's say two typical strategies are starting with some kind of a random solution. Let's say I'm looking at, I have this traveling salesman problem. I start with some kind of a random permutation. That's a fast way to get an initial solution, but the result may be that it may take more iterations to converge to some kind of a local optimal solution. On the other hand, I can define some kind of a greedy algorithm, which might take a bit longer to generate, but oftentimes leads to a better quality solution, or you reach the local optimum in, let's say, a smaller number of iterations. One thing to note here is also that using initial solutions with fitness values, of course, will not necessarily always lead to better locally optimal solutions after having run a local search algorithm. So just because my initial solution in one case is better than a different initial solution that I have, that I start with, doesn't necessarily mean that I will end up with a better overall solution in terms of this local optimal solution that my local search algorithm will give me. So it's always good to try different initial solutions and different ways of obtaining this initial solution. So that's something that's referred to as a multi-start local search. So find an initial solution, run your local search, then try again with a different initial solution. In terms of neighboring selection techniques, classically, in terms of a typical hill climbing or descent method, if we're talking about minimization, hill climbing would be a maximization. We exhaustively explore the neighborhood and we find the best neighboring solution is chosen if it's better than what we currently have. If not, we're done. So if we have a better neighboring solution, we pick that solution, we move there, and we keep going. Then we find again the whole neighborhood for our new solution, new current solution, and so on. The problem here is that it can be time consuming if we have large neighborhoods. So if you have, let's say, a very large solution space, a large vector of representing your solution, then where you have to try out all possible moves, then this can be very time consuming. Okay, another option would be to find the first improving neighbor. So let's say I start generating neighbors. So I have my solution. I start generating neighbors. Let's say this 1-bit flip. I start flipping bits. As soon as I have a neighboring solution which is better than my current solution, I pick it and continue again and start over. So start finding neighboring solutions for that new solution. So that's something that's referred to as first improving neighbor. So rather than looking at all possible moves, in which case, so the best improving neighbor would be, let's say, this deterministic approach. This can be also deterministic if, depending on how we specify this, the way in which we generate the neighborhood, and so on. Okay, another option would be a random improving neighbor. So let's say that I have either exhaustively explored the neighborhood or partially explored the neighborhood. I randomly choose one of the improving neighbors. So let's say I've looked at my whole neighborhood. I have n solutions within the neighborhood which are better than the one that I currently have. Rather than taking the best neighbor, randomly choosing one of these neighbors. So that could be one solution, which also can help us to avoid, let's say, getting stuck in certain locally optimal solutions. The best or the random improving solution in a reduced neighborhood, again, we reduce the neighborhood by, according to some strategy, so we only partially enumerate the neighborhood, and then we find either the best or a random improving neighbor. So these are just various combinations of different neighborhood selection techniques. But let's look at an example, a very simple example. Let's say we have a solution which is simply a number encoded in binary terms. So this is a value, an integer which is encoded in binary. The value is 10. We define our neighborhood as a 1-bit flip. So these are all the neighboring solutions of our initial solution. And now we look at different neighborhood selection strategies. So let's say we want to find the best improving neighbor. By the way, let's say we're looking at a maximization problem. In that case, we looked at the entire neighborhood and we choose the neighbor which is the best improving neighbor. It has a fitness value of 14. So our new solution is now going to be 1, 0, 0, 1, 0. If we were to look at a first improving and we generate neighbors as shown on this slide, so from top to bottom, in that case, as soon as we generated this first neighbor, we found it has a better fitness function, and we choose that as our new solution. If we were to look at this random improving approach, we have 3 neighbors which are better than our current solution. We randomly choose one of those. Or let's say that we generated only a reduced neighborhood, and out of this reduced neighborhood, again, we either take the best improving solution, which would be this one over here, or we randomly pick one of the better solutions. So that would be either this 14 or 11 over here. So this would be the best or random. Okay, so this was just a simple illustration of this neighborhood selection strategy. Any questions? Okay. Looking at just a classical, again, local search algorithm, steepest descent. So we're looking at a minimization problem. We generate an initial solution that becomes our somehow, either randomly using a greedy algorithm or so on. That becomes our initial solution. First of all, we have to specify what we mean by neighborhood. What is this move? If it's a binary vector, is it a 1-bit flip? Is it a 2-bit flip? Is it, if it's a permutation, is it some kind of a swap, or so on? So we specify what we mean by neighborhood, and we generate that neighborhood. We check all solutions that are in this neighborhood, where the value of that solution is less than or equal to, so we try to find the best solution in the neighborhood. So we're trying to find the solution such that the value is less than or equal to, again, this is a minimization problem, of all other solutions within the neighborhood. So this simply means that we're trying to find the solution with the lowest fitness value in that neighborhood. So we find the best neighbor. If it's better than what we already have, we stop. Otherwise, if it's better than what we already have, we update our current solution. Otherwise, we stop. If we stop, that means we have we've reached a locally optimal solution. If we were to look at it just visually, the local optimum will always stop at the first local optimum. So let's look at an example minimization problem. Our current solution is this little green dot over here. I'll move my cursor, my pointer away so it doesn't confuse you. So now we're searching, and we find our local search algorithm obtained this locally optimal solution. We came here, so this yellow circle represents our neighborhood. We checked the neighborhood of this green solution. There are no better solutions. Again, this is a minimization problem, and that means we are in a locally optimal solution. Of course, this is not necessarily the globally optimal solution. Let's say our initial solution is here. Now, let's look at neighborhood size and what I mentioned previously. So the neighborhood size is going to dictate also the potentially the locally optimal solution that you will find. So if this is a small neighborhood, this will be our obtained local optimum with this small neighborhood. So we started here, we checked all of the neighboring solutions, we're trying to find the smallest one, and we keep moving in that direction, and we'll move over here. What's going to happen if this is my neighborhood size? This is, again, just an illustration for, just to understand the concept better. But what's going to happen here? Am I going to find the same local optimum as in the case of the smaller neighborhood? Anyone?
We'll go left.
Okay, so we're going to go left because we're going to find a better solution over here, and we'll end up in this local optimum that was obtained with a larger neighborhood. So again, we see that there is potentially, or this trade-off between defining a larger or a smaller neighborhood. If we have a larger neighborhood, then computationally this is more intense, but we may be able to find a better solution. Okay, let's look at an example, a very simple example where we have this this function we're trying to maximize. In this case, a function we're trying to find the value of x, which is going to maximize this function. We encode it as it's an integer value. We encode it as in binary form with 5 bits, and we say that our initial solution is 10011, which will give us a solution or value of this function as 2,349. Okay, everyone's following me. So x is simply encoded in binary form. All right, so this is my current solution. My neighborhood is 1 flip. The first iteration, I find 5 neighbors. I calculate the value of the given function, which I'm trying to maximize. Now, what is going to happen now? What's the next step?
We take the result with the smallest.
It's a maximization.
With the largest value.
Fitness.
Yeah.
Okay, so we would choose this best improving neighbor. That becomes our new current solution. Okay, so let's see where we are now. So we found this best improving neighbor. It becomes our current solution. We found it by flipping the 4th bit, right? So according to our, with respect to our initial solution. So now this is our new solution, 1001. And this is the value of its fitness. We generate its neighborhood. So now we're looking at the neighborhood of this solution here. These are all the neighbors. Again, we're going to look at the neighbors, look at the evaluation function, find the best improving neighbor, that it's better than the current solution. It is. So clicking through this, okay. that new current solution was obtained by flipping the fifth bit. And now this becomes our new solution. Okay, this becomes our new solution. Now, again, we generate the neighborhood. These, we have, again, have 5 neighbors. Now what? What's going to happen now?
We stop.
Why do we stop?
We found the best solution.
So we don't have any solution within the neighborhood that is better than what we have currently. So in that case, our local search, if we specified it just as we simply did, ends at this point, and we have a final solution, which is a locally optimal solution. However, the global optimum, and at least in this case, is will give us a value of 4,050. So we have not found the globally optimal solution. Okay, just to illustrate, so there are many ways to improve local search. Very many strategies for this. First of all, as I mentioned, we can iterate with different solutions, and next time I'll talk a little bit about GRASP. We can change the landscape of the problem. We can, for example, use different neighborhoods, and again, next time I'll talk about something called variable neighborhood search. Or we can use an approach called referred to as accepting non-improving neighbors. So let's say I don't have any improving neighbors in my neighborhood, but the idea would be to sometimes, in certain cases, accept solutions which are worse than what we currently have, simply to escape from these locally optimal solutions. So sometimes it's, you know, you go a few steps backwards in order to overall to advance the search, and that's that's the basic idea behind the meta-heuristics taboo search and simulated annealing, that accept also worse solutions than the one we have in order to keep advancing the search. For example, multi-start local search. So let's say this is my first initial solution. I find the local optimum. My second initial solution over here, I find this local optimum. My third initial solution, again, I'm here, already found, and so on. So I can keep going like this. Okay, we have a few more minutes. The best seen solution is the final one, so I can go through these different, following a number of these different initial solutions, and having run different iterations of the algorithm, I can keep the best solution after that. Okay, I won't go into GRASP now, but I want to just say a little bit something about these fitness landscapes and what we mean by this. Just find where am I? So when we talk about search space, and I just wrote this out because I didn't have it on the slides. So we said the search space is defined as this directed graph where we have a set of vertices. These correspond to our solutions, and or which are defined based on our representation or encoding. So whether it's a binary vector or a permutation, or however we represent our solution, these are these nodes or vertices. And the set of edges correspond to the move operators used to generate new solutions. So when we say that there is an edge between two solutions, Si and Sj, that means that Sj can be generated from Si using a move operators, which means that they are neighbors. Let's say over here, I drew this picture. So let's say I have a binary encoding. This is my current solution, Si. And my neighborhood is defined as a 1-bit flip. In that case, Sj, there would be an edge between Si and Sj because they are neighbors. There would also be an edge between Sj and Sk, which is 1, 1, 1, 1, again, because they are 1 flip away. If I, on the other hand, I define my neighborhood as a 2-bit flip, then Si and Sk become neighbors, and these are not neighbors anymore. So that's what we mean by this graph of solutions and edges corresponding to these move operators. So what I want to highlight is that the different neighboring relations generate different search spaces and landscapes. So I have a certain search space. Depending on how I define this neighborhood, I'm going to specify how I'm going to move through this search space and what my search space is even going to be, right? which brings us to this notion of something called a fitness landscape, which you've likely heard of, which is defined by this tuple G and F. G is this graph, which represents the search space, and F represents this objective function that guides the search. So when we look at let's say, overall, this fitness, when we refer to fitness, it actually refers to kind of this landscape or height of or value that is assigned to a certain solution. When we look at different, we talked about different criteria when looking at designing a meta-heuristic. On the one hand, we want to diversify our search, and at the end of the, or an example would be random search. In that case, we completely diversify. We want to search various parts of the search space. On the other hand, local search is an example of exploitation or intensification, where we want to intensify our search within a certain area of the search space. Now, the question is, depending on this fitness landscape, how it looks, and we can think of it as in two-dimensional space or in multi-dimensional space. They're oftentimes kind of portrayed as some kind of a range of mountains where local peaks there's local peaks, there are valleys, and so on. The question is, what kind of a heuristic should we apply? These are some examples, just simply looking at this in two dimensions, of different, let's say, quality functions or fitness functions. On the one hand, let's say, so on the x-axis we have our search space. On the y-axis we have the value of our function. If we have, let's say, a fitness landscape or this valuation function that looks like this under A, what we have, unimodal. A good approach would be some kind of a local search or hill climbing algorithm, right? It will bring us to an optimal solution. And what we see is that we have a strong relationship between what we have on the x-axis, so these are the candidate solutions, and their quality. And by applying some kind of a local search algorithm, we will end up with finding an optimal solution. In this case, random search is a bad idea. So if your landscape looks something like this, then applying some kind of a random search is likely a bad idea. If we have something like this under B, and this is something that's referred to as a needle in a haystack. So we have many, many solutions which have the same values. And then somewhere out there is a solution that is much better than the others. In that case, hill climbing is not such a good idea, obviously, because you'll get stuck automatically. Probably random search is a better way to go. So in order for something like a local search to be effective, there has to be some kind of a gradient or an informative gradient which leads towards better solutions. If we have something like C, let's say a noisy, this is something referred to as a noisy example of a fitness function. Again, hill climbing or local search is a bad idea. Random search would probably be a better idea, because what we have is that even neighboring solutions that are close to each other differ greatly in quality. And this is something that we don't like to have, right? So when you think about designing some kind of a representation of a solution, anything that can smooth out this landscape will help actually the optimizer or the algorithm. Again, this is another option, another potential example, something called a deceptive curve, where actually some kind of a local search might take you farther and farther away from an optimal solution, which we see over here on the right side. So these are just some examples that I wanted to highlight. What are some, let's say, takeaway messages? The actual representation, the neighborhood, and the fitness function that we define will define this fitness landscape. What we want to do is we want to construct a representation that somehow smooths this fitness landscape or encodes the solution such that small changes, for example, a 1-bit flip, are likely to result in small changes in the actual fitness. So you can help, actually, in that way, you can help your optimizer. What I showed, I listed this over here. You've heard of using gray code. So let's say we want to encode an integer as a binary vector. This is the actual value, the phenotype. This is the encoded version in binary terms. What we see here is this classic problem where, for example, the values 7 and 8, which are near each other, are actually 4 bit flips away. So they are, in terms of, they are not neighboring solutions in terms of this. You need a large number of moves for small change in fitness. Gray code is a different way of encoding where we have this property that just by simply flipping 1 bit, the solutions are 1 bit away. So this is something that's important also to highlight. So again, the important thing is that we have design actually this the algorithm or the representation such in the neighborhood that we have some kind of a efficient way of searching this area. Okay, since it's 4 o'clock now, I'll stop here and continue next time. So I have some more takeaway messages at the end of this lecture, and also I'll go through GRASP next time. What I want to just mention before we end for today, actually, wait, let me just stop recording for a second and then I'll don't go away yet. Hold on.